Welcome to lesson 5 of 7 on assessing the accuracy of remotely sensed data. In part 4, we talked about an overview of thematic accuracy, sort of introducing the topic. And in part 5 here, we're going to talk about reference data collection. So the objectives of this lesson really only about the components of an effective reference data collection. So we're going to talk about classification scheme, the sample unit, the sample size, the sampling scheme, the source of the data, the methods of collecting the data, the timing of the collection, and then ensuring consistency and objectivity. So there's a lot of material here. This lesson will take a little bit longer, but it could take 10 times as long as this to really understand every little detail of this. Okay, so if you need more information, there's lots of sources you can go to. So reference data collection. If you look at the flow chart that we talked about in the last presentation, you remember this. We talked about the classification scheme. We talked about reference data collection as far as sampling, and we talked about other considerations. And so we're going to go through these step by step and make sure that you have a good feeling and awareness of what's going on with these different issues. So the classification scheme is absolutely key. We're doing thematic accuracy assessment. We're talking about assessing the accuracy of the themes, of the classes, of the map classes, land cover, vegetation types, whatever it is that you're talking about. And so you need to make sure that you agree upon this very early in your project. You can't wait till the end or the middle to figure it out. And if you have a client, you have to make sure you and the client both understand what these classes are, that you agree on them, and everybody's happy with that. Okay. A classification scheme is used to categorize the Earth's surface, right? Okay. So every good classification scheme has 4 components. It must have not just the labels, but it must have some kind of rules to define that so that everybody agrees what that class means. So for instance, for a forest, forests are defined by the density of the trees, how close together they are, or sometimes that's called crown closure, but it's also defined by the height of the trees. Okay, so maybe it's 3 meters. Anything less than 3 meters is not a forest yet. Okay, but if you don't define those things, what you think is a forest and what I think is a forest could be very, very different. Okay, so very commonly you see lots of labels. It says water, it says vegetation, it says grass, whatever. But if you don't define it, then everybody doesn't have the same understanding of what we're talking about. So I can't emphasize that enough, that you've got to start with the classification scheme. Okay, you also want your classification scheme to be mutually exclusive and totally exhaustive. Mutually exclusive means that there's not confusion between categories. If you're on a place on the map and then you go to that same place on the ground, everybody's going to agree what that category is based on the rules or definitions or dichotomous key or whatever you use to define those classes. Okay. You also want your scheme to be totally exhaustive. Totally exhaustive means that every area on your map is going to get a label. Okay. Sometimes we use other or unclassified to make sure that that's the case. Okay, and that would be fine if a small 0.5% of your map turns out to be other or something like that. But if half your map is other, it means that you haven't defined your classification scheme very well. Okay, so mutually exclusive, totally exhaustive. And then the last property that's really nice to have is that it's hierarchical. And that is, you start with very general categories and you go to more specific details. And so you can collapse, or you can go up and down the hierarchy depending on what level of information you need for your different applications. It also means for your accuracy assessment that you may have 3 levels in your classification scheme, and at the 3rd most detailed level, you have 30 different map classes, but you simply can't afford to collect enough reference data to assess all 30 classes. But at level 2, which is a little more generalized, maybe you only have 12 classes, and you can afford to do that. So you might do the accuracy assessment at 12 classes at level 2 and say, my assessment's been done at level 2. Here's my map at level 3 if you're interested in that, but all I can say is something about the accuracy at level 2. So having a hierarchical scheme has some great benefits. Okay, let's talk about sampling. So there's 3 components here, right? Sample unit, sample size, and sample scheme. When we were talking about positional accuracy, sample unit wasn't an issue, but it very, very, very much is here, okay? Historically, many projects, more than half the remote sensing projects that you'll see have used an individual pixel to assess the accuracy of a map. That's a bad idea. It's absolutely not recommended to do that. Why? Because you cannot accurately locate an individual pixel on the ground or on the map, okay? There's registration error on your map, plus or minus 5 meters, 10 meters, 20 meters, depending on your imagery. And there's inaccuracies on the ground due to, GPS location problems and things like that, okay? Individual pixels are usually smaller than the minimum mapping unit. We've talked about minimum mapping unit previous to now. And so you don't want to assess something smaller than your minimum mapping unit. So for those reasons, individual pixels should absolutely not be done. If you look in the literature, you'll see it's done all the time, and that's really unfortunate. It's wrong, okay? What you really want is a cluster of neighboring pixels, a grouping, okay, that you put together then becomes a single sample unit, okay? So often a 3 by 3 homogeneous area, okay? And the cool thing about that, if it's homogeneous and you go to the center of it, you eliminate positional accuracy issues, okay? If you go in the center and you've got, some problems locational wise, if it's homogeneous, you're still going to be inside of that 3 by 3. Okay? That way it can be accurately located. You also need to place those homogeneous samples away from edges because, again, you get that locational problem. You do not want positional error in your thematic accuracy, okay? So very, very important. These days, it's also becoming more common to use polygons or segments or objects because of object-based image analysis. And so there's a whole field developing of object-based accuracy assessment as a result of that. But please, I can't emphasize enough, no single pixel accuracy assessments. Okay, sample size. Rule of thumb, 50 samples per map class. Okay, again, we talked about this a little bit with positional accuracy. They require 20 samples per map class. I suggest 30. Here we really need close to 50. If you get down around 30, you're starting to push it, okay? Below 30, no, it's not going to be valid. Okay, you're just not going to have enough information. There are some equations that you can think about for this if you want to. If you're talking about not building an error matrix, but you just want to calculate right and wrong, okay, so just overall accuracy, yes or no, then you're talking about a binomial distribution, okay? 2 cases, yes and no, or right and wrong. But once you start talking about the error matrix, you're talking about a multinomial distribution where you have 1 possible right and then n minus 1 possible wrongs, where n is the number of classes in your map, okay? So the multinomial distribution and that rule of thumb work out pretty equally, and either way, you're fine, okay? But you need to have enough samples. You need to make sure you have a good distribution across your map as well, and that's where it comes down to your sample scheme to think about that, okay? Remember that the cost of collecting reference data is expensive, okay? So sometimes it's prohibitive, okay, and you can't do it. So what are the alternatives to that? Well, you can use less than 50 samples. Got to be careful. If you get less than 30, then it's really not worth it. You start to become really statistically compromised. Or, as I mentioned earlier, you can collapse upward in your hierarchy, okay? So you have less classes, you're able to collect 50 of fewer classes instead of 50 of all those level 3 or level 4 classes. Hopefully that makes sense to you. What about the sampling scheme? So sampling scheme involves deciding how the sites are going to be chosen. You've decided you need 50 of them. You decided they're going to be these 3x3 homogeneous grouping of pixels. Okay. What else do you need to think about? Well, you need to think about the level of spatial autocorrelation. You also need to think about the level of difficulty for obtaining reliable reference labels. And you need to think about, your budget. So there are a number of considerations here. Again, trade-offs that you're doing. And then you've got a lot of different choices for sampling strategies. You can use simple random sampling, although that's not recommended because it tends to oversample in the large categories and undersample in the categories that you only have a little bit, small proportion of, but those might be the categories that you want to know the most. So most people do a stratified random sample where they stratify by map class, set some minimum number of samples per map class, and then have the randomness within those classes. That's a really good thing to do. Okay. Cluster sampling, a lot of people do some cluster sampling because it's hard to go everywhere. Okay. Or you may be in a situation where, you fly into a place like Alaska, the helicopter lands, two guys jump out with shotguns to ward off the bears, and the other two people, collect the reference data. Okay. Collecting data in a cluster there where you're trying to get things similar, around you in a shorter distance. Okay, maybe, right? Systematic sampling, we like systematic sampling. You pick an interval and then you have a random start and then you take a sample every, 2 miles or every 300 meters or, whatever it is that you're trying to do. That works okay. You have to be careful that there's not some periodicity in your data and that you end up sampling along that period and as a result have a problem with your data that you've collected. And then there's lots and lots of variations of these. But I would say that most people these days are doing some kind of stratified random sample. This is really an issue with randomness, and it's one of my favorite slides. And you can see that it's not uncommon that you get stuck behind a fence, the gate's closed, you have to cross a river, here you got to go across the canyon. Randomness, pure randomness can create lots of problems and can be incredibly expensive to collect a purely random data set. Okay. At the same time, you can't just go every place that it's easy and not get a set of samples that's representative of what's going on. So again, you've got to have a little statistical knowledge here. There's trade-offs. You got to be careful what you're trying to do. Don't forget about spatial autocorrelation. If you don't remember the definition, spatial autocorrelation occurs when the presence, absence, or degree of a certain characteristics affects the presence, absence, or degree of that same characteristic in neighboring units. Okay, we all know about correlations. This is not correlation, this is autocorrelation. It's relationship with itself, the same characteristic. In our case, we're talking about errors and patterns of error, and we're talking about that over distances, okay? So neighboring units. So if I make an error in one place and my data is very positively autocorrelated, then samples nearby are more likely to have error in them. Okay? And so I want to make sure that I spread my samples apart. Okay? Take care of spatial autocorrelation. So we need to consider how that error is distributed so that we can deal with that. If we're more likely to make an error in close proximity to another error, then those errors are positively autocorrelated, and you need to take that into account. And the way you take that into account is you space your samples apart. We talked about that in positional accuracy. You would do some kind of similar thing. You would set some kind of distance measure and make sure that you don't take samples too close together. What about some other considerations? What about the source of the data? Okay, we all would love to use existing reference data. Okay, it's very, very, very tempting to use existing reference data. You have to be careful. Is the sample unit size of that existing reference data sufficient? Often it's too small and therefore not good, not appropriate for using for accuracy assessment. Sometimes it's a different classification scheme and you've got to crosswalk it. Sometimes it's too old, okay? So there's always the temptation to use existing data, but it rarely works out for you to be able to do that, okay? So what else can you choose from? Well, could you use other remotely sensed data? Could you use some more higher resolution remotely sensed data, whether that's digital or analog, whatever, okay? Or do you have to go to the field? Okay, well, if you go to the field, you're going to get the best results from the field, but it's very expensive to go to the field. You certainly get more accurate species identification if you're looking at vegetation. However, you don't get a bird's eye view, right? You get a view from below, not a view from above. And, as we've already talked about, it's difficult to go out and do all of this, okay? What if you use some remotely sensed data? Well, that's nice, more readily available, less expensive. It provides a bird's eye view for sure. However, it's less accurate, right, for species identification. So in some cases, using digital remotely sensed data or other remotely sensed sources is all that's possible. It's all that's available. Okay, you're doing, something where you're mapping the agricultural crops around the world. You're not going to have the time or the money or the resources to go and send out data and go out to the field everywhere in the world to do this. Okay, so lots of things to think about when you're talking about what's my source of reference data. Okay. All right, how do I collect it? So how I collect the reference data is really highly dependent on the classification scheme, the level of detail or the complexity of that scheme. Sometimes I need to make measurements. Sometimes it's okay to just take observations. So I'm in the field. What do? So observations are quicker, they're easier, they cost less, but they're typically not as accurate. If I go and make measurements, then I'm much more confident of my answers. I get superior results. However, it takes a lot more time, and by far they're the most expensive. I also have to worry and think about observer variability here. Okay? If more than one person is collecting my reference data, then how do I control that? Everybody's got little biases, training, experience that they have, that especially when they're making observations, we have to make sure we get consistency. So that's important. When do I collect the reference data? Okay, really two choices here. Sometimes I need to collect the reference data at or very close to the time that the imagery is being collected, right? It really depends on how fast things are changing for the map classes that you're trying to classify. For instance, if you're doing agricultural crop mapping, especially in areas where they're growing 2 or 3 different crops in a year, you can't wait 2 years to collect the reference data. It's just not going to be any good anymore, okay? So you have to be really, really careful about that, okay? You want as cost-effective, training data as possible. So sometimes you go out there and if you have to collect the training data when the imagery is being collected, you want to make sure that you can also get the reference data for accuracy assessment at the same time, okay? So that it's nice to be cost effective that way and be able to do both things. However, if you do that, if you collect the reference data for training and the reference data for accuracy assessment, which have to be independent of each other, if you collect those at the same time, there's really no way to ensure that you have collected enough samples per map class, and therefore you actually might have to go out again, okay? So sometimes you collect the reference data after the map has been made, okay? That way it's easy to get enough samples per map class because you have the map readily available to know what you need, okay? However, it is more expensive because now you've done 2 trips to the field, right? One for training to collect that training data so you can make the map, and now a separate independent one to collect the accuracy assessment data. And then of course you have to be careful because things can change between the date of the imagery and the collection, especially as that gap between those dates spreads out. Now, some of those things are really obvious. If you have a forest and somebody goes in there and harvests the forest, when you go out there, it's going to be very clear on the imagery that it was forest, and now on the ground it's not. So Things to think about, just things you have to be aware of. Okay. Already mentioned that you need to be consistent and objective, especially if you have multiple people collecting the reference data for you. But even if you're by yourself, it's good to have these procedures set up to make sure you ensure consistency and objectivity. In order for the assessment to be valid, you need to make sure that the reference data is as correct as possible and certainly unbiased. Okay. So how do you do this? Well, you want to make sure that there's independence between the map and the reference data, right? You can't look at the map and say, oh, this is forest. Okay, I'm going to go here because it's a forest. Oh, I got that one right. Okay, you can't cheat like that, yes? It has to be independent. The reference data has to be collected with no knowledge of the map at all, okay? It requires that you have objective and repeatable procedures. A nice way to help you out with that is to use some kind of a field form. In the old days, we tended to use more paper field forms. These days, we tend to use, some kind of tablet, our phone, laptop, some kind of data logger, some kind of electronic device. Okay. We want to make sure that we implement the sampling design. We've talked about sampling designs that's as unbiased as possible, and that we collect enough samples to make sure that we, have a statistically valid result. And then we need to employ quality control procedures during data collection and any data entry that's done to make sure that we don't introduce error here. Okay, so again, hopefully as I'm talking about all these considerations, you're thinking about how these are actually sources of error, okay, if I don't do it properly, if I don't think about it ahead of time. All right, so what did we accomplish in this lesson? Well, we discussed the importance of the classification scheme, so you should really understand that that has to be done at the very, very beginning of the project, right? We looked at the issues for sampling, including sample unit, never use a single pixel, sample numbers, we need to make sure we get about 50 samples per map class, and then the sample scheme, we talked about randomness and the issues with that and other sampling schemes that are possible. And then we looked at all the other different considerations that you need to think about. The source of the reference data, how you collect it, when you collect it, how you can achieve consistency and objectivity. So really, really important that you're aware of all these considerations when you're planning out your accuracy assessment, because as we've just said, you can introduce all kinds of error if you're not thinking about these things ahead of time. Thanks for joining.